Assalamualaikum and good day everyone. Today my group will share a simple overview of our PBL assignment 2 titled Wastewater Treatment for Dye Removal. For this assignment, there are 3 members in our group, Aisyatu Alisa, Balkis and Nurul Izzati. Together, we study how adsorption can be used to remove dye from wastewater. In our project, the main contaminant is textile dye. These dyes are organic compounds that give colour to products such as leather, paper and some food processing material. When the wastewater is discharged without treatment, it makes the water colour and polluted. To remove this dye, we use an adsorbent called walnut shell activated carbon, which is WHAC. Waste walnut shell are treated with potassium hydroxide so they become very porous. Why we use WHAC? Because of the high surface area and good adsorption capacity. This material can capture a lot of dye molecules efficiently. Then, I will explain how does adsorption work. Adsorption extracts contaminants through a phase transfer separation process, avoiding harmful chemical additives. We can see the old way and the adsorption way. The old way using chemical breakdown process and the adsorption way using phase transfer separation process. So why we use adsorption way? Because a highly surface process where solid materials provide a binding site for pollutants, acting as a physical trap rather than a chemical reagent. Then, I will explain the 4 successive stages and adsorption. The adsorption process can be explained in 4 main stages. First is mass transfer. Dye molecules move from the bulk solution towards the absorbent particle. Second is boundary layer transport. They pass through the thin liquid film surrounding the particle. Third, intraparticle diffusion. Molecules diffuse into the internal pores of the adsorbent. The final one is binding to active site. The dye molecules attach to the active site on the surface and are effectively removed from the water. These 4 stages show how walnut shell activated carbon can work as a simple, low cost and effectively method for treating dye contaminated wastewater.
Now, I will present the 2 primary stages that allow this material to effectively purify water. The first phase of the process is the travel stage, scientifically known as diffusion. During this stage, dye particles such as reactive blue 19 navigate through the water to enter the filter's microscopic internal tunnels. It is important to understand that this is the slowest part of the entire process. As the outer surface becomes saturated, the particles must wait to move deeper into the charcoal. However, our research shows that by warming the water to 50 degrees Celsius, we can provide an energy boost that allows these particles to jump and travel more rapidly, significantly reducing the total cleaning time. Once the particles have traveled into these tunnels, we reach the sticking stage, or adsorption. Here, the dye adheres to the charcoal walls through natural magnetic light attractions. The remarkable efficiency of this filter is due to its vast internal architecture. To put this into perspective, just 1 gram of this walnut shell charcoal contains an internal surface area of 2,347 square meters, which is approximately equivalent to half of a football field of space packed into a single teaspoon. This immense surface area allows the filter to trap a record-breaking 1,227 milligrams of blue dye for every gram of carbon used.
Moving on to the broader impact of this technology, we have evaluated our absorption system through both an environmental and societal impacts. Looking at the clear advantage alongside the challenges we must manage, first on the environmental front, this approach champions a circular economy by transforming agricultural waste biomass into highly sustainable absorbent that leave a minimal footprint compared to traditional methods. Second, it provides powerful pollution control by removing stubborn dyes and pigments from industrial wastewater. We protect aquatic ecosystem from severe threats like eutrophications and the disruption of photosynthesis. However, we must note the production and disposal challenges. The chemical activation process can be energy intensive and generate emissions, while spent adsorbents pose a risk of secondary pollution through leaching if not properly managed. From a societal and economic perspective, The primary benefit is public health protection. This system eliminates toxic, mutagenic, and carcinogenic dyes, ensuring clean, safe water for both present and future generations. Economically, it offers distinct advantage. It is far more cost-effective than complex alternatives like ozonation, flocculation, or photocatalysis, utilizing cheap materials with reusable regeneration cycles. That said, we face real implementation hurdles. Moving to industrial bulk production brings scale-up and long-term stability challenges, and their large-scale facilities can spark public opposition regarding site selection, underscoring our need for clear technical communication with the community. Okay, next for the recommendations, we propose 3 core recommendations. First, we must optimize regeneration methods for the absorbent materials. Developing highly efficient, repeatable reuse cycles is absolutely critical to lowering long-term material costs and preventing spent biomass from turning into waste. Second, we need to directly address large-scale implementation challenges. This means tackling the technical hurdles of bulk production, optimizing large facility footprints, and proactively engaging with the public to build community acceptance. Finally, we recommend integrating absorption with other treatment processes. Absorption is incredibly powerful, but combining it with secondary advanced treatments or even emerging technologies like AI-driven process controls will maximize overall efficiency and ensure sustainable, comprehensive wastewater remediation. That's all for the recommendation.
In summary, utilizing walnut shell derived carbon is an effective, economical, and sustainable method for water purification. By repurposing agricultural leftovers into a high-performance cleaning tool, we can remove industrial pollutants without the need for harsh chemicals. This process is not only eco-friendly but also yields rapid results, clearing complex industrial dyes in approximately 150 minutes. That's all from my group. Thank you.